Okay, in this video we'll be going through Newton's gravitation, and in a level 3 context, this is mainly going to apply in the context of circular motion. So we know from level 2, when we are talking about circular motion, if we have an object moving in a circle, this blue object right here, we know that there is going to be a centripetal force which is accelerating it towards the center, correct? Now we know our Fc is equal to mv squared over r. Now we know that this centripetal force is not a real force, it's actually provided by another force, right? This could be tension, friction from the road. Now for our context of gravitation, we can start looking at what is providing that centripetal force for a satellite, let's say. Now this brings us to the thought experiment of Newton's cannon. Right? And so if we have a cannon on the ground, right? This cannon is going to shoot a projectile. It's going to follow a parabolic curve. There we go. Now if we zoom out a bit, right? And we see that this cannon follows the arc of the Earth. So that's the arc of the Earth right there. So this cannon is going to be quite big now. You can see that the parabola that the projectile follows matches the circumference of the Earth. And so if we make this Earth completely rounded now, right? So that's Earth. And we put our cannon up top, like this, we can shoot a projectile and it follows the parabola of the Earth perfectly till it comes back around and hits the cannon again. And so theoretically, this will work, provided there is no friction. And therefore, because there is no friction, the projectile will be in constant freefall. So we can see here that there is a force that's providing the centripetal force for this cannon projectile to go in circular motion around the Earth. And this is our gravitation. Now, Newton's Law of Gravitation states that there is a force between two objects. We can call these M1 and M2. The force between M1 and M2 is directly proportional to the product of M1 and M2, and inversely proportional to the square of the distance between the center of mass of M1 and M2. Right, so based on this definition, we can create our formula, and that formula is Fg is equal to M1 times M2 all over r squared, and also multiplied by our gravitational constant. So as you can see from that definition, we see that the force is directly proportional to the product of the two masses, that is this section right here, and also inversely proportional to the square of the distance between the center of mass of M1 and M2, which is this part right here. And we also have our gravitational constant, G. So this right here, Fg, is a force, obviously, and that's therefore in newtons. This r squared is the distance between the two center of masses, and that's in meters, obviously. And these masses right here are both in kg, and this gravitational constant has a value of 6.67 times 10 to the negative 11, and has a unit of kg to the minus 1 m cubed s to the minus 2. And if you want, you can do some dimensional analysis to figure out that that is actually true. Okay, so now moving on to an example. We can find the force between two people that are 2 meters apart. So if we have a person right here, and this person weighs 75 kgs, and a person right here let's say this person raised 60 kgs and they are 1.2 meters apart, let's say. If we use our formula, Fg is equal to G times M1, M2 all over R squared. We know that our G is 6.67 times 10 to the negative 11 times 75 times 60 all over 1.2 meters squared. That gives us a force of 2.1 times 10 to the negative 7 newtons. And as you can see, that is incredibly small, and that is why we don't perceive it when we're standing next to someone. Also, one thing to note, that this 2.1 times 10 to the negative 7 is the force that M1 is acting on M2, and also the force that M2 is acting on M1. So it is a Newtonian force pair. And if you remember, that is a key condition for Newton's third law, that both of the forces need to be a force pair. Okay, so we have another question here. We can use Fg to find the acceleration due to gravity on the Earth's surface at sea level. That's an important statement there. The radius of the Earth would be different if we're up on a mountain, right? Because that extra distance needs to be accounted for. So we're at sea level, so we don't need to worry about that. So the way we can do this is we can equate the weight force to the gravitational force. And we know the weight force is just mg, and our gravitational force is gm all over r squared. Now, as you can see, I've changed the equation slightly. I've used big M and little m to swap out for m1 and m2. Just a different notation. You'll see that quite often as well. So as you can see, we have m on both sides, so we can cancel those out. And therefore our g is just equal to the gravitational constant times the mass of the bigger object, which is the Earth in this case, all over r squared. And so we can plug in our numbers. Our g is equal to the gravitational constant, which is 6.67 times 10 to the negative 11, all over the mass of the Earth, which is given up here as 5.97 times 10 to the 24. And that's all over r squared, which is 6,370 kilometers. So we have to put that times 10 to the 3 squared. And that indeed gives us a value of 9.81 meters per second per second. There we go. So we know that that is the value of g, right? And as we were talking about before, because this is at sea level, again, if we were up on a mountain, let's say Mount Everest, this will increase our radius. And therefore, if it increases our radius, that means g will be a smaller value. And therefore, the acceleration due to gravity on Mount Everest is actually slightly less than on sea level. So you can do that calculation if you want. You can search up the height of Mount Everest and add that to the radius of the Earth if you want, and see what value you get. Okay, so now we'll be moving on to a situation where we have the Earth, right, call that E, and we have the moon, call that M, and this blue dot on both the Earth and the moon is where the center of mass is located. Now, if we look back at our definition, we know that the Fg is inversely proportional to the distance between the center of mass of the two masses, right? That's that r squared. And so, if we were to calculate the Fg of this system, this r value is not this distance right here. I repeat, it is not that distance right there. It is that distance plus this distance and this distance, because r is the distance between the center of mass of m1 and m2. So in this case, it's the distance between the center of mass of Earth and the center of mass of the moon. And so you need to take into account the radius of the Earth and the moon in these situations. And that's pretty much it for part 1. We can move on to part 2 next.